students, welcome to Radiographic Film. We're going to be covering the characteristics of film today. This is a film library, and we used to have to take an image like a chest x-ray. We'd have to go into the film library and pull the jacket for the patient. There's colored stickers on there and according to their medical record number, and we'd pull the priors for the radiologist. Several objectives for this PowerPoint. Go ahead and take a look at those. I'll upload the PowerPoint for you. We're going to talk about the different types of film as we get towards the end of this. It may be a separate lecture depending on how quickly I can get through this. So, as we know, Rankine was the first person to discover X-rays using a glass plate. We no longer use that technology. The glass plates, as you can imagine, were difficult to maintain, and I know I'm really clumsy. I can imagine I'd be breaking these plates. They required really high doses of radiation, and a flat plate term came from that. So if you ever hear technologists say, go shoot a flat plate, they're talking about an abdomen, and it came from using glass plates. They went to a cellulose nitrate. During World War I, as you can imagine, glass plates wouldn't be very handy. The problem is the cellulose nitrate was very flammable. It led to a lot of really big, devastating fires. They switched to a cellulose triacetate, and about the 1920s, that was less flammable, but the films would warp with age and didn't hold up through time. So now they're using a polyester base. That's what we're using currently for places that still have film, and is introduced in about the 60s, to give you an idea. Okay, so film construction. You have your base layer, then adhesive, emulsion, and then a super coat. We're going to cover each one of those. So the base is about 150 to 300 micrometers, and is semi-rigid polyester with the lucent blue tint in it. It has the adhesive layer on top of that, and the emulsion is anywhere between 3 to 5 micrometers. The emulsion is a gelatin with silver halide crystals suspended within it. On top of that, there's a protective coating. With the film base, it's polyester, like I talked about. It's flexible yet durable, and it's strong enough for us to be able to pop in a view box. It's uniformly radiolucent, that's very important, and film must retain its size and shape throughout the use and processing. So we call that dimensionally stable. The thickness ranges anywhere from 150 to 300 micrometers, and the newer films is about 175 micrometers. They add a blue tint as it reduces the eye strain for the radiologist and helps with the accuracy. So the color is added during manufacturing. There's a thing that's called the crossover effect, and that's where the film base is coated with a special substance to prevent light from one side of the screen crossing over through the base and blurring the image. So it's like a reflection, and I'll show you the pictures here. It makes more sense when you see that. So this is a double emulsion film. Here's your base. There's emulsion blue on this side, emulsion blue on the other side. So the base is treated so that when you take an exposure, the base blocks it from exposing a double emulsion film. So that's important. That's called the crossover control. So review. The film base is polyester. It provides structural foundation for the emulsion layer. It's flexible and durable and dimensionally stable. It's uniformly lucent, and it's about 150 to 300 micrometers in thickness. The adhesive layer, it binds emulsion to the film base and allows for proper emulsion distribution over the base throughout processing, used to prevent bubbles or distortion when the film is bent during process and handling. And we'll cover when we go through the processing how much stress is put on that film as it goes through the rollers. So it allows emulsion and the base to maintain proper contact and integrity during use and processing. So it's important that we have a good adhesive on there. The emulsion, so there's a lot to this. It's the heart of the film. It's composed of silver halide crystals, and they're suspended in the gelatin. So it's homogeneous, and the active ingredient is silver halide. Typically, it's between 3 to 10 micrometers in thickness. Now, one book says 3 to 5, the other book says 5 to 10, so we'll go from 3 to 10 on your quizzes. So the gel suspension, it's a non-reactive medium which chemicals can penetrate to process of silver halide crystals. It distributes the crystals evenly over the surface of the polyester base. It keeps the silver from clumping together, making one area more sensitive to radiation than the other, so it keeps it uniform. It must be clear so light can travel through uniformly, and it's made of gelatin like what we eat, but a higher quality. X-rays interact with this layer to form the image. So silver halide crystals are embedded uniformly in this clear gelatin. So the clear gelatin, the crystals are silver bromide, and it's about 95 to 98 depending on the manufacturer. Silver iodide is about 2%, and sometimes there's silver chloride in there. So silver iodobromide is name used as emulsion, is made of two silver bromide and silver iodide. Now I'll show you the structures. All must take place in total darkness. So when they're manufacturing film, it is in complete darkness. So the different levels of manufacturing. So there's the crystal production, the ripening, the mixing, and the coating. So here is a typical structure. You can see the silver, which is the Ag, and the Br is bromide, and the I is iodide. So silver halide crystal formation. So this is a process. So pure metallic silver is dissolved to nitric acid, forms silver nitrate. Silver nitrate is combined with potassium bromide. Silver bromide will precipitate out, and the potassium nitrate will be washed away as a waste product. So the gelatin must be present for these crystals to form. So tubular grains are flat, 2 to 4 times larger, and can be more evenly dispersed in the emulsion. So the shape of these crystals is really important. The advantages of having this shape of crystal is absorption of a great proportion of exposed photons, so that's big. Reduces light crossover, which we talked about crossover already. Reducing silver coating requirements, and 45-second processing. The downside to that is that now it's really sensitive to any kind of developer and replenishment rates. So when we talk about processor, you'll understand that a little bit better. It'll come together. So here's the different shapes of the crystals. Here is a silver halide crystal. As you can see, the lattice formation up here, and that's just in one little area. So silver halide crystal structure. Resultant shape can be varying, as you know. However, the inner structure takes on a cube form and a lattice form. It's bound together by moderately strong ionic bonds, with silver as being the positive and bromide and iodide as being the negative. So the crystal structure permits both free silver ions and free electrons to drift through the lattice. So each one of those little areas that we showed, the silver iodide lattice, that has a sensitivity spec. So the silver gold sulfide creates imperfections within the crystals. So what that does is it gives good imaging properties, and it allows for collections of many silver atoms in one area after being exposed to light or X-ray photons. So result, sensitivity center or sensitivity spec within the crystal lattice for imaging exposure. That's where we're getting the blackness on the film. So your structure of your silver bromide, it's not perfect in size and shape. It's responsible for chemical contamination of silver sulfide. So the silver sulfide is introduced by chemical sensitization into the lattice. It's usually near the surface, and we call that the sensitivity center. So photoelectrons and silver ions are attracted to these sensitivity centers, and they form the latent image center. So that's where your metallic silver, when you process, is going to be seen. Ripening. So ripening is the length of time the crystals need to grow. So the size of the crystal determines their total photosensitivity. Longer the ripening, the larger the crystal or the grains, the more sensitive the emulsion. So looking at the graph here, if we look at the crystal size small with resolution, it's going to be high. And with your speed, it's going to be really slow. So the crystal size, as we go larger, your resolution is going to drop, but the speed is going to be faster. So you have to look at that and understand that as you change your crystal size, the speed of your film is going to change. Also, in your ripening, the potassium nitrate is water soluble. So after the ripening is complete, emulsion is cold, shredded, and washed, and it removes the potassium nitrate. Mixing. So shredded emulsion is heated and melted to specific temperatures and sensitize the crystals, and several extra ingredients may be added, such as dyes, so the blue dye, a fungicide or bactericide, antifogging agents, hardeners, whatever is needed. So films are classified as panachromatic, which is sensitive to all colors, and orthochromatic, which is sensitive to red color. So the dyes are controls, they control that with the dyes that they're adding during the mixing phase. Coating. So requires precise and expensive equipment. There's only a few factories in the world that can do this. They generate 40-inch rolls of film, and they have the adhesive layer is applied to the base, then the emulsion, and these 40-inch wide sheets of film, then the super coat is put on top. They're then cut to size. This whole process is done in complete darkness. So this super coat or overcoat is a protective layer of the gelatin. It provides the sturdiness to unexposed radiographic film. It has an anti-static in it, which is really good. Next week you'll get to see some of the artifacts that display on film. It reduces damages from scratches, pressure, and contamination during storage, handling, and processing. So, silver halide crystals. The differences in speed, contrast, and resolution depends upon the process by which the silver halide crystals are manufactured. From the time the emulsion ingredients are brought together until the film is packaged, the whole process occurs in darkness. So, what's the answer on the test? It's done in complete darkness. So, film emulsion, the different ways. Chemically created silver halide emulsion layer. So, with contrast, as we talked about, it's observable differences in the grayscale. So there's multiple levels of contrast depending on the film and what we're looking for. So contrast of an image receptor is inversely proportional to its exposure latitude. So the range of exposure techniques that produce an acceptable image. So the other thing I want you to look at here is high contrast, smaller silver halide crystals, and low contrast is larger. Think of resolution, it's kind of the same. So speed, how fast it reacts to x-rays. So the speed is the sensitivity of the film. It will also talk about the size of the grains that are embedded in the silver halide. So here we go back to this. So if we talk about the crystal size was small, we have high resolution, but it's going to be slow. With the large crystal size, we have low resolution, it's going to be really fast. And then we talk about our emulsion layer. If we have a thick emulsion layer, we're going to have a higher resolution, but it's going to be slower. A thin. It's going to be higher resolution, but slower. And same thing, if we have a thick layer, it's going to be low resolution, but it's going to be a lot faster. Okay, so the types of films. We are going to go through. Here is our direct film, and that's where there is no screens. It's just high radiation dose, high detail, usually used in dental and biopsies, single emulsion, extremely fine grains of silver halide crystals, and it has a high silver content. It has a thicker emulsion, typically 2 to 3 times thicker than medical film, and it requires some kind of manual processing. Screen films, that's what you'll be using in the lab, and it's when you're using intensifying screens with the film. It's a reduction of dose. You get a wide variety of speed, contrast, latitudes, and resolution. And with larger crystals and thicker emulsion, usually provide lower contrast, wide latitude, and less resolution, with faster with double emulsion while reducing in silver content. That's important as we talk about silver recovery. Mammo film and fine detail film. It's fine grain, single emulsion paired with a single intensifying screen. Usually the opposite side has some kind of light absorbing. Laser film, laser is used and it's sensitive to that laser color, and it's extremely accurate with no distortion. Duplication film, It's pre-exposed and it's put one on top of the other and exposed.